In the next example, we're going to look at how to compute probabilities of compound events. And the first example, or the first little lesson that we had, was how to calculate probabilities of simple events, both theoretical and experimental. And now we're going to look at the compound event. So in review, an event that has a single outcome, such as rolling a 6 on a die, is called a simple event. Many problems involve finding the probability or a composite or compound event. So the word compound kind of triggers us to think about, it says more than one event. So it says if it's a compound event, it consists of 2 or more simple events put together. So we could ask it not 2 things, but 3 things, and we can expand on that idea. To find the probability of a compound event, you must consider whether the events can occur at the same time. Now that's going to be a pretty important concept here. So we're going to have to reason whether or not these events can occur at the same time or not. So that's where our thinking is going to have to come in. Events that cannot occur at the same time are said to be mutually exclusive. Mutually exclusive events have no outcomes in common. For example, because it is not possible to draw a card from a standard deck that is both a king and a queen, these events are mutually exclusive. They cannot happen at the same time, so they're called mutually exclusive. They are excluded from happening at the same time. It is possible to draw a card that is both a king and a spade, so these events are not mutually exclusive. So they're showing you in some Venn diagrams what mutually exclusive means. There are no kings that are also queens, but if they are not mutually exclusive, we can find a king that is a spade, and there's your exception to the rule. It has both qualities. So we want to make sure that we can make a distinction between if they can both occur at the same time or if they simply cannot. If they cannot occur at the same time, the vocabulary is mutually exclusive. So what we're going to do is we're going to look at calculating compound probabilities. Our key concept says there's some addition rules for probability. If we want to know if one event occurs after another, then we've got to be able to look at using an addition rule for probability. So here's the layout. If 2 events A and B are mutually exclusive, which means they can occur at the same time, then we can calculate the probability that event A or event B occurs is equal to the sum of the probability that event A occurs alone plus the probability that event B will occur on its own. So we're going to look at adding the 2 different independent probabilities together to figure out what the chances of one or the other occurring. But we also had to reason another way too, because not all events are mutually exclusive. So the second point in our key concept, if 2 events A and B are not mutually exclusive, the probability that A or B will occur is the probability of A or B is equal to the probability of A plus the probability of B. It looks very similar to what we had for mutually exclusive with a new addition. What's the probability of both A and B? So now this probability of A and B, we need to understand what that is saying. What's the probability that it is a king and a spade? So that's our 1 king out of all of those. So we're going to end up subtracting anything that is in the intersection or the overlap of these Venn diagrams. So a lot of times I'll represent these with a Venn diagram. They're easy to draw, and you can quickly see which things are in the intersection or the overlap, where they are both characteristics, a king and a spade. Where in these, if they're completely independent, then you will not see any overlap, and you'll not be able to have a king and a queen at the same time. So let's take a look at an example that they're talking about here. Determine whether the events are mutually exclusive or not mutually exclusive. Then find the probability. So we're going to look at 2 different examples of this. Keisha has a stack of 8 baseball cards, 5 basketball cards, and 6 hockey. If she selects a card at random from a deck, what is the probability that it is a baseball or a hockey card? So I've already put a Venn diagram together here. What I want to do is look at the labeling on this. What I want to do is I want to represent the cards that she has. She has 8 baseball cards. So I'm going to put in here, we've got 8 baseball cards. This next thing, she has 5 basketball. So 5, now I got to use it a little different. So I'll just use basketball. And then the last one, she has 6 hockey cards. Now there's no overlap and no chance of a card being both a baseball card and a basketball card, or a basketball card and a hockey card. So these things are called mutually exclusive. They can't occur at the same time. So in order to calculate the probability of getting a baseball card or a hockey card, and the key word here is or, I want to figure out what's the probability of, I'm going to go A or B, and then I'm going to put it in context of our problem. What's the probability of getting a baseball card or a hockey card. So our definition says, in our key concepts, if we want to find the probability of A or B, then we do the probability of A plus the probability of B, and if they're mutually exclusive, which in this case they are mutually exclusive because they can't be both, hockey and basketball or vice versa the others, that's all we need to calculate. So first thing we're going to do is, what's the probability of getting a baseball card, and then we're going to add together what's the probability of getting a hockey card. So let's look at our number of favorable outcomes. So now we're calculating probability. In order to figure out the probability of finding a baseball card, we figure out how many baseball cards there are, of which there are 8 favorable outcomes out of the total number of outcomes. So now I got to do some little totaling. We have 8, 5, and 6. So that's a total of 19 outcomes, plus the probability of getting a hockey card. Well, there are 6 favorable outcomes. There's 6 hockey cards, and there's still 19 cards. So that's a total of 14 out of 19. And we could convert that to a percentage once again. If that were a big issue, then I would go ahead and do that. But a fraction works just fine. So, second example. Suppose that 1,400 students take Spanish. Suppose that of 1,400 students, 550 take Spanish, 700 take biology, and 400 take both Spanish and biology. What is the probability that the students selected at random take Spanish or biology? So I'm going to put it in the context of the problem right away. We want to know what's the probability that they take Spanish or biology. Now, before we can calculate any of these or statements, we have to figure out whether it's mutually exclusive or not. So right away we know that we've got students that are taking both. So there are some students in this overlap, and I've represented that in the Venn diagram that I've created prior to getting here. So we've got some students that are taking both. We know in this universe, a lot of times we like to talk about the universe as our Venn diagram. There's 1,400 students total in this entire rectangular box that represents our situation. And I'm going to label one of these as our Spanish students. So I'm going to do this one. This is our Spanish, and it has 550 students in it. We've got 700 that take biology, so I'm going to put my biology, let B represent biology, and there are 700 students taking biology. But then there's also some that take both. And in this intersection, or the overlap, is where they are not mutually exclusive. So we know we have 400 students that take both. Now those would get counted twice if we weren't careful about subtracting them out. So that's why this rule is going to be the probability of taking Spanish plus the probability of selecting one that's in biology minus the probability that they're in Spanish and biology. This part here is the overlap where these 400 would be getting counted twice. If we said how many students are taking Spanish, we would have to include those 400 in this circle. And if we asked how many people were taking biology, we'd have to count those 400 in this circle. And that means these 400 got counted twice, or double. So that's why we're going to subtract out this double counting that we have here. So what are we going to end up working with? What's the probability that a student takes Spanish? Well, of our 1,400 students in our universe, that's our number of possible outcomes. The probability of getting a favorable outcome being a Spanish student is 550, plus the probability of getting a biology student. There's 700 favorable outcomes of biology students out of the 1,400 total students that are possible to select. And then we want to select or subtract that overlap where they are 400 of those students that are in both biology and Spanish. So that's 400 out of 1,400. A lot of times I'll use the word both on that. Are there any possibilities that they could be both in Spanish and biology? Yes, there are. In the previous example, could you have a card that is both baseball and basketball? No, you cannot. So that helps you figure out if you use the word both to help determine the type of probability that you're up against. So we'll do the addition on these. This is 1,250 out of 1,400 minus our 400 out of 1,400. And then if we do our subtraction on those, that should be an 850 out of 1,400. Okay, so we're looking at calculating a little bit more complicated problems where it's conditional probability. And if I guess Maybe one of the other things we want to do with these is reduce them as far as you can. I'll give you a little plug on the use of your calculator. If you're not real fond of reducing fractions, you can definitely use your calculator to do that. You simply type in your 850 divided by 1,400. You can say equals, and you can hit your math key, and you can have it change it back into a fraction. At this time, the fraction will be in lowest terms. So our probability in lowest terms on this one is equal to 17/28. Conditional probability, determining mutually exclusive or not mutually exclusive. That's a big part of that lesson.